Chapter 3 review questions for this is for Year 11 prelim. I have to find these files first, so that'll take a second. I did download them yesterday, so it shouldn't take too long. Answers to prelim review 3. I'm not going to have the clues open at the same time. Just know that there are clues to the prelim reviews that don't have the full answers, but they have the page numbers. Is there a way that I can scroll around this? There we go. Okay, sorry, so there's the answers getting ready, but then I also want to have the textbook open as well so that we can look at that at the same time. We'll do that in a new tab, and we're finding Chapter 3 questions. So I haven't actually posted this in the Google Classroom yet as homework. I need to do that, but it should be okay. I'll probably make this due at the end of the month. So for those of you who are looking at this now, you'll have about 2 weeks to do these questions. But I'm going to go through the answers now, so that could help. I'll make this a bit bigger because I know sometimes these things aren't easy to see on screen. So there looks about right. Make actually this a little bit just so I can click back easily into the my tabs, and make the text a little bit smaller. Okay, I think we're about ready to go now. Okay, what development in motor cars led to the need to replace the block brake? What was the replacement? Well, I'm going to rely pretty heavily on these are my answers that I've typed, and that helps me to make sure that my answers are going to make sense, and that I'm not just going to be rambling. It's better for you. Block brakes needed to be replaced as they were incompatible with the pneumatic or air-filled tires. So rubber tires developed by Dunlop, I want to say in 1880. Wait, that's not a tab. I'm used to there being a tab there. We'll just go from off this one. We'll go just like that. People are like, I don't care when Dunlop invented the tire. 1888, there you go. It's interesting to note that the company that we now associate with Dunlop tires was named after the dude, but it was not run by him, I'm pretty sure. Don't quote me on that, that's never going to be a HSC question. Okay, what was the replacement? So we replaced the block brake with the contracting band brake, and then from the contracting band brake we went to, that's sometimes referred to as an external drum brake, and then we had an internal drum brake, which I'm going to say was Louis Renault in 1902, and then we had from there we went to disc brakes. Okay, so you can find the answers for that on page 89. Okay, so who invented the drum brake and what year did this occur? Well, I just said this, so you did get me. Yeah, I was like, maybe that's an unnecessary detail, but there you go. I was a little shaky about, but the thing is, this question, you're not supposed, this is not a test. These questions, the expectation is you can go back through the book and look these things up. I personally would never write that sort of question. I try to avoid, so my mum is a teacher, and she always talks about when writing exams, we should avoid things that rely on just recall of facts. That's not really what we're here to teach. We're here to teach understanding of concepts, or to assess understanding of concepts. And in the case of something like who invented the drum brake, that is a fact that has no real universal application. That if there was an alien species that also invented the drum brake, all we care about is how effective they are. We don't really care about the history of what happened. Okay, that said, we often need to know the sequence that things are developed. We often need to know the time period. And when I say time period, you might remember at the start of the year, I group things into fairly simple terms like prehistoric, ancient, and prehistoric sounds like it's, cavemen, but prehistoric just means it predates writing. Ancient means during the time of writing before the printing press was developed. And then that leads us all the way up to, say, the Industrial Revolution. The Industrial Revolution, I kind of consider World War One to be where I consider, because there was two industrial revolutions. I think the era that we consider the post-industrial revolution goes all the way up to World War One, where we saw a massive mobilization of engineering power to produce engines and steel and those sorts of things. I personally think the interwar period is relevant, and then World War Two. This is a lot of answers that aren't the answer that you're looking for. So hopefully, if you're watching this not live, you're using the skip button. Okay, why was the drum brake superior to its predecessors? Now, in this case, they're talking about the closed drum brake and not the contracting band brake. And the reason why it's advantageous is because it doesn't get affected by debris or the weather and dirt, those sorts of things. Yep, that's it. Replace less frequently. There's also some things to be mentioned that, like the contracting band brake, it only worked in one direction, so that's another downside. Because cables only really can apply force and tension, so that when you start rolling the other way, the cable doesn't provide any tension. Again, we're getting into minutiae now. So I guess really, if you're looking at this video and not just looking at whenever I click the answers here, really you should expect there to be a lot of minutiae, but we'll try and keep on the hopefully everything I say here is relevant to somebody. Anyway. The coefficient of friction is a ratio between which two values? In my Year 12 class, I drew a picture explaining this recently. So what we know is, yeah, I am going to go to Paint. I mean, the short answer is the coefficient of friction is F equals mu n. So if we rewrite that question, that equation, F equals mu n. So if we rewrite that, writing things is bad. This is with a mouse. F equals mu n. So if we rewrite that equation, we're going to say the friction force, or the reaction due to friction, the friction reaction is equal to the normal. We can see how we rewrote that equation. That the friction force divided by the normal reaction equals mu. So if I have a box and there's some weight, mass times gravity going down, and assuming that we've got a regular box like this, we're going to have that be our normal reaction. Okay, and then I'm going to push it with a P, and then I'm going to have friction opposing that. We often we use an angle, theta, and theta is equal to we can also say that the mu is also equal to the tan of phi, right? So it's this ratio of opposite over adjacent. So the friction force over the normal reaction also gives us this angle. I keep saying theta, it's actually phi. So that's what we're doing there. The brake pad forced against a disc by 500 newtons is shown. Determine the braking force created if the coefficient of the brake pad is 0.38. So that's the ratio. I mean, I'll go into some more detail there. Remember, blue stuff is stuff that you don't need to know. I must have skipped a question about asbestos. Why is asbestos still allowed in brake linings in Australia? That's a good question. Asbestos was banned in Australia for all vehicles sold after 2003. However, many cars sold before this date. This is not the case worldwide. Aftermarket parts produced in other countries, including the US, may still contain asbestos. It is important to remember that all brake dust is dangerous, and yeah, you don't need to know about how other brake pads, brake dust is dangerous, I don't think. Yeah, okay. So, okay. so in this question here, sorry, going back to question 6, no, question 7, 500, so it's pretty simple here, right? F equals mu n. I've written it in a different way, just so that you're familiar with different ways it can be written. The HSC formula sheet writes it as F equals mu n, but friction force, normal reaction, pretty easy, just typing stuff into a calculator. Okay, so the next question is question 8, this one here. Now, I'm not going to go through this in great detail because a lot of people did this in their engineering report. So it's a pretty obvious choice here. But there are a couple of ways we can approach this question. One way is that we can do it as a 3-force method. And I've done lots of 3-force methods. I don't know if I specifically have done this one for the class. But what we'll do is we'll just quickly delete that. Take this picture. Screen print. Okay. That's good enough detail. Okay, so what we can do with our straight lines is we know that we've got 3 forces acting here. We have a reaction on the pin, we have a line forcing outwards here. Now, we can make a reasonable assumption. We can say, well, if we're pushing this has a component, is this going to the left or the right? It's going to the left, so that means this is going to have a force pushing out to the right. That's a reasonable assumption, and so we're going to then draw in this line up here. And so with that, we've now found OMG, the point of concurrency. Yeah, not yet. And then, once we've found the point of concurrency, we'll make that one green. Now what we can do is we can move these lines around to create a force polygon. So, like I said, let me just extend this line. Okay, and then I'm going to draw a new line. Sorry for this, that's a bit slow. Now, we know that one's going down because they've told us that. They've given us an arrow. And we're pretty confident this one's going out here. So we need to continue. So either they're all going clockwise or they're all going anti-clockwise because we're going to assume these 3 forces are in equilibrium. Now, the issue here is we need to draw a line that is parallel. And I don't think... Ah, nice. I can continue that line. And what's more is I can probably even copy it. If I can... No, that was a shame. Okay, I thought I could copy it. What we'll do is we'll just extend it. And then we'll take this line and extend that. You get the rough idea. So with this diagram here, if we know the value of this is 300, if we know this is 300, well then we can calculate the other values of the force being applied. So this is going to be like 3, 6, 9, probably about 1200, and the same concept. You should use a ruler and measure it off and do the scales accurately, but that's the idea of how you do that using the 3-force method. There are analytical solutions. Let's see what I've typed in for you. Okay, so for question 8, this is a 3-force method question. First, you find the point of concurrency. Second, draw the line. Third, draw the line parallel. I said it was 1200, 1300 is pretty close. That was me eyeballing. So yeah, that's the reaction force. This force here that's pushing back. Okay. determine the force in the caliper pistol. So, because they don't really care about this force up here. Okay. What is the tensile stress in a brake cable of diameter 2 millimeters if the tensile force is 200 newtons? Okay, so stress we need to know is stress equals force over area. They haven't given us an area, they've given us a diameter. Now, engineers, and I remember when I was in high school, my teachers kept telling me that, use pi d squared on 4, and I'm like, I'm not going to do that. I've learned pi r squared, and I'm sticking with it. That's fine. Do whichever one you like. There is a point, though, where you do realize that just switching over it will actually save you time. So, it didn't go in a whole lot of working out there. Okay, so let's have a look. I'm just curious if I don't think I can duplicate this. I can, that's nice. Is this book 2? Yeah, looks like questions 2. Oh, here we go. So that's how they've solved it. You can see they've done the 3-force method. And there they go. They've gone force over area. So force, they've given pi d squared on 4. So they've said pi d squared on 4 is pi times... Funny that they say that, and then they've gone, oh no, they've moved the 4 up here. So they've rewritten the equation. So remember that it's 0.02, right? So they're using, I just want to make sure that we're using the same units, right? So they're writing that as 0.02, whereas this is millimeters. So the millimeters, the diameter is 0.02, the diameter is 0.02, whereas it's actually 2 millimeters. So 2 millimeters should be 0.002. That would be my take on that. Okay. So we're finding stress equals force over area. Now, keep in mind that it's also a point that I like to say all the time. Wow, I did something wrong. Or it's the wrong group, maybe. Oh dear. Titanium. It'll be on here, so I'll just use this one. I did have this set up so it would be nice and easy, and it'd have all the notes that I posted for you guys, but I don't really want to pause. The picture I'm looking for is we go together like megapascals and millimeters squared. So if I get my calculator, I do really hate this calculator. I did talk about in my last stream that I might do something different in the future, but where are the other tabs? Did I even close that tab? Oh, that's opening an edge of all things. Huh. Okay. So stress equals force over area. So we're going to find the area first. So I would do the area as pi d squared. So d squared is 4 times 3.14 divided by 4. Okay, which I know is a bit silly, but when we have, so 2 times 2 is 4. When you divide by 4, it's 4, so we're going to get pi, right? And then we're going to do force divided by our area. So, and that makes sense, right? 2 millimeters squared is going to be pretty close to, when you think about if it was a square, it would be 2 times 2 would be 4. A circle occupies pi out of 4 percentage, so like 78% of that square. And then, so force divided by area, so we've got 200 newtons. Now it's important we always use newtons, divided by 3.14 equals 63 megapascals, because we go together like megapascals and millimeters squared. You can say it the other way. I had a class where they wanted to say millimeters squared and megapascals. I like that. I like my way. Anyway, so we get 63. Now, if I go back to the book and the answers, they say 63. I don't know how they get that answer, if that will work out or not. because I think that's wrong. But you know what? I'm too lazy to check, and it might maybe an errata. And you know, Copeland's been doing this longer than me, and I'm not going to hold it against him if he did make a mistake anyway, because writing textbooks is hard. Okay, car is traveling at 80 kilometers per hour when the brakes are suddenly applied by, and they lock to the side of the wheels. The coefficient of friction of the wheels is 0.6. Determine the distance it takes to stop for the car to stop. Assume that the car slides in a straight line. Okay, so you know what I'm going to do? I'm going to make this small this way as well, and so I can get back to things. Could be a bit of a risky click, but we'll see how we go. Do we have stopping? Not on here. I have to go to an older one. Calcium. No, older still. Potassium. Here we go. Okay, so this is how we work out stopping distances. They do talk about this in the book. Am I going to duplicate this again? I really need to put in an ad blocker because I don't need that ad. Stop. That's what we want to do. And then we're going to go to titanium, which is the current class. And then we're going to go to media photos. Okay. So, yeah, if we can get the other edge window, this one here, and duplicate it. Might have to do something weird like that. That might work. Okay, what page number did we say it was on? 167. There we go, 167. There must be a few pages that don't count. They go through the answer on page 167, but we want where it's being discussed on 104 and 103. We need to probably add on 10 pages. Okay, stopping distances. Here we go. So here's how they calculate it. We're going to use, I think that the animation you see there, I think relates to, so can I open this in a new window? So I don't actually use any figures here. I just say that this is the calculation. I wonder if I can make this bigger at all. Duplicate again. And then go to videos. And then go to this potassium. Okay. I'll just pause it when it gets to the end of the video so it doesn't do some silly autoplay. Okay, that stopped. Cool. So, can we see that? Okay, so they've added in values. For me, I just think it's easier to say, okay, so they've gone S equals V squared divided by 2 mu G. So how do we get to that? Well, first of all, we start by saying that work equals energy, right? Energy is the ability to do work. Ergon, literally, like ergonomics, is working in a comfortable way, and energy means ergon in. Energy is the ability to do work. So a formula for work is Fs, right? And the formula for energy is K equals half mv squared. I do sometimes mention the actual past papers. Let's go with this one. Okay, so these formulas, you don't need to memorize this. Work equals Fs, that's there. Kinetic energy equals half mv squared. You don't need to memorize that. That's given. Once we have that, I mean, you do need to understand though that that's where we start. So once you know that work equals half mv squared, sorry, kinetic energy equals half mv squared, What we can then do is we can start substituting. So we can replace F with the friction formula mu n, right? We can do that. And then, well, in this case, because we're not on a hill, we're on a flat surface, we can substitute n for mg. So this is what we've got here. We've taken work, Fs, and we've replaced the F with mu n, right? That's where we've got there. And then we've placed n with mg because it's on a flat surface. So that way we can get this formula here. V squared equals 2mgs, right? That's another way of writing the formula, probably a nicer way, but we want to rewrite it because we want the stopping distance s. So then what we can say is that mu mgs equals half mv squared. The masses cancel out. We can remove them from both sides, and that leaves us with half velocity squared divided by the coefficient of friction times gravity. Once we have that, it's pretty easy just to start. So here we've said in this case, Rn or mu, the normal reaction equals mg because it's just a flat surface. It's a boring question. And that gives us this formula. Now, this is a pretty hard question. If I were to include this question, it would be, where would I include this? It might be a good question for like number 20 on the multiple choice, just because that way I can give you a couple of options. It's only worth 1 mark, and it really tests people's knowledge. And the thing is, you can derive this from first principles, and it is explained in the textbook, but I don't think I've seen any questions like this, but it's not a bad question. I will tell you though that when I first started teaching and when I wrote these answers, it really took me going through the book to understand what's going on here. So I will say that I've never put one of these in the test before, but as I look at this now, I'm like, you know what? It could be a good question 20. Okay, moving on to the exam, back to the book. Where are we? Okay. Okay, I'll get that back in. So, just want to try and make it so that I can get back to and from things quickly. Sorry about that. Draw a stress strain curve for mild steel, label the proportional limit, the upper and lower yield points, and the UTS. You don't need to see me draw that. What we'll do is we'll actually have a look at what the book says, and the book says on page 100, it has that information. That's how we draw the stress strain graph for mild steel. What we can also do, just to value add a little bit here, is we can go to our testing. Have we done testing as a post yet? I'm sure I've posted Mr. Rockwell, the hammer as he's known to his friends. I'm sure people are screaming at me, he's there, he's there. This is the second time I've been unable to find that picture, and I'm sure I posted it recently. Okay. Okay. So if we look at a tensile test, this is how we determine.
The material opposes an increase.
This is how we produce these graphs, that we stretch a piece of metal and okay, so when they finish the graph, that's a sample for mild steel. But typically, if we just look at mild steel graphs, we can see there's always this wonky part here. That's the telltale feature of mild steel. We can draw more of a stylized graph. So the way that this one looks in the textbook is absolutely fine. No one's going to be too critical of what you've drawn here, but this is fine. So what it asked us to label, I think, was, let's go back and look specifically at what did they ask us to look at. They said, draw the proportional limit, the upper and lower yield points. Okay, so what is the proportional limit? The proportional limit is where it stops being a straight line. So we know that Young's modulus is the gradient of this curve, right? It's the stress divided by the strain, or the change in rise divided by the change over run. While that gradient is constant, right, it's going at a set proportion. Now the elastic limit, we don't know where that is. We have to be told the elastic limit, but the elastic limit we can assume is effectively at the proportional limit. The elastic limit is slightly different. The elastic limit is where it will no longer return to its original shape when the load is removed. The upper yield point is the top line here. The lower yield point is that there. Now those four points, I will say I was teaching for a couple of years before I really understood the difference of those things. What we typically use in any sort of, what we use at uni and the practical applications in my working life is we just care about the lower yield point. That becomes our effective working stress. And when you buy a material, I mean, for steel, I just always use 300. I'm pretty sure that was always the standard for the mild steel we used. I can't remember ever using anything else for structural steel. For reinforcing concrete, we used 450. And I'm pretty sure that was set more by the code rather than by suppliers, but I know that they did update it to 450 in my time at uni. So it may have been, I've now 10 years out of the game, so it's possible that that's changed, but just to give, it's sometimes useful to have some sort of point of reference. Okay, so what is the difference between elastic and plastic deformation? Well, we talked a little bit about that there before. Elastic deformation means that when you remove the load, it returns to its original shape. Plastic deformation means that it permanently is changed. Now, the example I always like to use is metal rulers. I think this is just a really salient example for school students because everyone at some point has had a metal ruler that some kid in class has gone doing, and I discovered that metal rulers have an amount of spring to them, and then someone else has been an idiot and gone and bent them. Working with metal rulers in our tech rooms, I tell you that we often have kids who bend them. So, not often, but often enough that I think that seems to be a universal concept. So the idea is that while it's still doing to its original shape, that's elastic, whereas once it's bent and it no longer bends back, or even if it has some amount of deformation, that's plastic deformation. Permanent deformation, that's plastic deformation. States Pascal's principle. Pascal's principle of hydrostatics says that two sealed vessels containing a fluid will have the same pressure in both. That would be my answer there. Why is it important to hydraulics? Because it can be used to apply a mechanical advantage. Let's see what I said here. All the stress, yeah, that one's fine. The pressure in two connected closed systems must be equal. I have enclosed liquid. I would maybe change that to a fluid because I think it's true with gases. Yeah, there we go, fluid and the container walls. It's used in braking. It didn't ask about in braking, but so I would still give this corrected in an exam because I say, oh, we use it in master cylinders, but because it gives mechanical advantage is the actual reason. Okay, what is steel? Steel is a ferrous alloy containing predominantly iron, which is where it gets the word ferrous from Latin, and some amounts of carbon. Usually, like we talk about, less than 2% carbon, right? Usually, there you go, up to 1.4% carbon, I like even more accurately. Okay. Describe the difference between austenite and ferro. Okay, so austenite, for starters, only exists at high temperatures. Austenite, by definition, can't exist below 723 degrees, and depending on the carbon content, could be a lot higher than that amount. So austenite is soft and ductile. It's still a solid, but it's soft and ductile, whereas ferrite is can exist at room temperature and it can hold a much smaller amount of interstitial carbon. I think it's a pretty good definition. Let's see what they have to say. Austenite, I didn't talk about the crystal structures. That was the easiest answer. Yeah, okay. What I said was absolutely correct, but the crystal structure is a great way of differentiating them. Okay. Explain what perlite is. Perlite is a lamella, which means layered. It exists in layers. So another way of saying that is perlite consists of layers of ferrite and cementite. Perlite contains 0.3% carbon and is a lamellar mixture of ferrite and cementite. Yeah, that's good. Okay, I didn't mention the carbon content. So at that percentage we get full perlite, but I guess it's true to say that perlite always contains 0.83% carbon. That's probably true. What happens to steel, the hardness of steel, as the amount of cementite increases? It gets harder up to it gets stronger only up to around about the eutectoid point. After about 0.8, it doesn't keep increasing its strength, but it does keep on increasing its hardness all the way up to that 1.4% carbon. So that's the answer. The hardness increases as cementite increases. It's badly written, and I would no longer agree with that stronger component, but past me wasn't as smart as current me, or as knowledgeable at least. Describe what martensite is. Martensite is a circular or body-centered tetragonal crystal of steel that is very, very brittle and very, very hard. What I say? I talked about how it's produced. I said it has an acicular crystal-like structure that's very hard and very brittle. I didn't mention BCT, so Mr. Fink will appreciate that. Upon cooling FCC, austenite transforms into BCC. Explain why. Oh, okay, here we go. Explain why rapid cooling BCT forms. So body-centered tetragonal. I don't give a great answer there. I just say it doesn't have enough time for it to form the structure. That's why BCT occurs. Yeah, that's okay. It's hard to answer a good question there. I could see you could write a multiple choice question there. You could say that why does rapid cooling of austenite form a BCT structure? And then you could say something like, because there's not enough time for it to form a BCC. That could be the sort of thing that you could give as a multiple choice. I've said many times, I don't really like to include BCT into exams because I just don't see it very often in HSCs. Why is manganese added to steels? I'm going to tell you that these sorts of alloy additives, I'm not going to include. And that's just because, again, I just don't see them enough. Toughness and hardenability. Okay. Why is nickel added? Corrosion resistance. Why is molybdenum added to nickel chromium steels? I'm pretty sure it's hardness. Improves material properties at high temperatures, used in aerospace applications. Yeah, okay. Hatfield steel. What is it used for? What is it and what is it used for? Explain what is different about its structure at room temperature as opposed to plain carbon steel. Hatfield steel is used in the teeth of excavators because it's hard. It has a hard outer and tough core. Okay, but I didn't actually answer the question of what is Hatfield steel. I thought Hatfield steel had molybdenum in it, but I could be wrong there. Let's have a look. Yeah, it has manganese. Manganese, molybdenum. The reason why I remember this is, I'll give you another application, which is a bit silly, is that I name all of my groups, my student groups, after elements. And so my current year 8s, they're manganese, and there isn't really much used in manganese. Interesting reading this, that manganese might be used in aerospace. The current picture I have, because I was thinking of Hatfield steel, is I have this World War One helmet, which, and I think about mangoes. So it's not a great answer, but yeah, excavator teeth is another option. And yeah, molybdenum was aerospace, so I could have excavator teeth made out of Hatfield steel. I just couldn't find very many good pictures, but maybe excavators sounds cooler. That was the best picture I could find for. Like, even looking here, I can't really see. I'll tell you what, if anyone finds me a good picture for Hatfield steel, I will take that on board. So it's like the backhoe bucket is made out of Hatfield steel. Yeah, maybe that's better than World War One helmets. I'm currently using World War One helmets. Okay, so what is the difference between cast iron and steel? Cast iron has a higher carbon content. It has it can be cast more easily than steel. It has good compressive strength. It also, because it has graphite, it can be, the more graphite it has, the more it can be machined easily, excuse me. And it also has vibration dampening. The silicon produces graphite, and graphite has these benefits. I just talked about the carbon content. There we go. Okay, different kinds of cast iron. Carbon appears in different forms in cast iron. How does it appear in white cast iron and grey cast iron? So, without looking at the answers, I mean, I looked at it very, very briefly then, but I don't remember it. White cast iron, I think, just has lots of cementite. Grey cast iron does have, because it has lots of cementite, whereas grey cast iron, the excess carbon, I think, appears as graphite, and that means we have more pearlite. Let's have a look. White cast iron consists of large section of cementite. Grey cast iron contains graphite formations. Yep, I'm okay with that. To be honest, I don't think that you're likely to get questions. I'm not going to write you questions on this. Again, it's just I don't see it enough in the HSC for me to give questions on this. Okay, how does SG, which is spheroidal graphite cast iron, and CG cast iron differ? So, what have I got? This is 20. Oh, which type of grey cast iron is stronger? Coarse, fine, or coarse? Fine grey cast iron is stronger than coarse. Spheroidal graphite is stronger than compacted graphite, but it does not have as good vibration dampening. Again, all of these questions, look, I'm happy for them to be revision and they're things to know, but it's not the sort of thing that I would write in tests. So don't lose sleep studying these. Black heart malleable cast iron has free carbon present in what form? Rosettes. Black heart. Yeah, forms in rosettes of tempered carbon. White cast iron. White cast iron doesn't have what free carbon is present in white heart malleable cast iron? It's only the interstitial carbon in ferrite, I would have thought. Let's have a look at the answer. White cast iron does not include free carbon. Boom. Because it diffuses into carbon dioxide and it consists of typically entirely ferrite. Look at me knowing stuff. I mean, I have been teaching this for several years, but I don't really go through these answers all the time. This is like a COVID special. So anyway, why is copper added to brake pads? Heat transfer, I'm pretty sure, is the answer. Yep, heat dissipation. Dissipation is a better word, but transfer is correct. Which type of resin is used to bind brake pads together? Phenylformaldehyde. Yep. Is a thermosetting polymer resin used to bind brake pads? Okay, draw two stress strain diagrams, one showing high toughness, the other one displaying high strength yet a brittle failure. So we're done with that. Delete. What we're going to draw is boom. So that's our graph. The one with some toughness would look like that, and the one with high strength but brittle failure would look like that. Something along those lines. I said see page 120. In terms of as the cementite increases, you notice that our strength actually decreases, but our hardness keeps going up. So I think that's worth pointing out that as cementite increases, strength actually decreases. It almost makes my answers wrong there. So a little bit of a take back. I wouldn't lose sleep over that though. Here we've got our spheroidal graphite and our compacted graphite. Here we have our White Heart's malleable cast iron. I make my references to Dragon Ball, how he goes like through this is the third form in order to produce White Heart. What page was I looking for? 120. I've gone too far. Got just too excited about things. Maybe I didn't go too far. I was looking at the wrong page numbers. Here we go. This one is tough. This one is brittle. Okay. 4 hardness tests that are available. So the most important one is Rockwell. Oh, sorry, I hadn't been looking at anyone's okay. Oh good. Just checking that there was no. Okay. So what are the 4 hardness tests? Well, I mentioned before I had the picture of Sam Rockwell. Problem is I can't click here without pressing those buttons. So Sam Rockwell for the Rockwell hardness test. If we click on this, we should actually see what a Rockwell hardness tester looks like. I have one at school. It doesn't work anymore, but we do have one.
Machine.
I think we looked at like the cost of replacing them now, repairing it is like, why would you bother? And especially these days, I mean, I would never do the test. I would just always show you.
Then he picks up the gear.
I think you get as much out of watching the YouTube video. Anyway, the difference between, so the Rockwell test is the default, but there are different tests we use. We also have, what I'll do is go back with scandium, where's titanium? There are different tests. I don't need that anymore. So there's also, Rockwell uses a conical test, I'm pretty sure. I talk about it in this video here on my YouTube channel. Let's see if we can find the tests. Then we talk about stopping distance. All that stopping distance stuff I mentioned.
Way of writing half is writing something over 2, and that's a cleaner way of writing that.
We're talking about Pascal's principle.
No one's expecting you to memorize that formula. We expect you to be able to figure it out from first principles. So,
where's the testing?
Where's the testing? What do they give you? They tell you this. They say that work equals force times distance, which equals the change in potential energy plus the change in kinetic energy. That's what they expect.
Oh, no, it's not on this picture, of course. No, because that one's the coefficient of friction. Testing, who we got? Okay, so to list them really quickly, right? We have Rockwell, which is the default. We have Brunel, which is the ball from the before times. We have Vickers, and Vickers is for the thin metals. And just yesterday, I watched Lethal Weapon 2, which you've never seen Lethal Weapon 2. It's a very good movie. I'm trying to do my South African accent, and I think that's that's still acceptable in this day and age to try and do a South African accent. But
okay, so why do we use it? Well,
there's different kinds, so they show the different different applications and the different. They all use shaped
Testing
fittings. I'm
looks
pretty sure
almost
Vickers
exactly the
is a
same.
pyramid
What's the
shaped.
difference between the two of them? Well, we use Rockwell. It doesn't leave a big mark, so we can use it on a finished
Brunel
test
is
because it
a
doesn't
ball
leave a big
shape.
circle.
Here we go.
What is
That's
the
the picture I'm looking
comparison
for. Vickers is pyramid shaped. Brunel is ball shaped. Rockwell is conical. That's the adjective. And then we have things like the Shaw scleroscope, and we use that because it's portable. And here we can see someone talking about chocolate that's harder than steel. So they're using a durometer, which is where the reference to Shorty, like a melody in my head, which my kids like. Okay, so that's the tests that are available. I think that's it. We're done. Geez, we did that pretty quickly. Okay, so I had a student ask, is there any way they can check their answers? Yeah, okay. So there are answers in the back, which I mentioned just briefly. The thing is the only answers that we have are for calculations. And so for chapter 3, there's only 10 that have working out. But for everything else, I do have answers here, which I've been referring to as we go. I will put those up, but I don't like to put them up before if I'm in class and I'm allowing people to write answers by hand, then that's fine. But here I won't put them up until I've made the homework due. And the reason for that is because there are a number of times where I've had the answers that students have submitted. They've even kept the same color, like the blue color that I include, just to show like the clues and things. Do remember, so I'm more than happy to give you the answers, but do remember that I have instead something to help you out, which is uploaded already, clues to prelim reviews, and that has all of the page numbers where you can find, I mean, for some of them I do actually have the full, you can see here I have the full answer, but I have the page numbers to say where you can find the answer, and hopefully that's of some value. But if you're really keen, you can go through this video and go back and look at the answers after you've completed them. Nope, the clues for prelim review have everything in there. It also has chapter 4 as well. Look, it is a pain, but the idea is you should make a reasonable attempt on your own of how to do these questions, and then once you've answered them, the other thing you can do, if you were really keen, you could submit them to me and I could go over them and mark them for you. But the other thing I would suggest is if you have someone that you and a friend could both work through them, and then after you've written your answers, you could then do a cross-check so that you could swap your answers and then see that if you both get the same thing, we could probably be fairly confident that you're right. Whereas if you get different answers, then you can go back to the video, and I mean, at the very least, I'll at least go through them in the logical order. I'm not doing question 9 and then question 17 or something like that. Okay, so yeah, look, and definitely it's worth mentioning that there are some of these questions here that really are, look, there's nothing here that's not relevant. And it's just a question of whether or not it's relevant if it's likely to be relevant for the HSC. Now, I've never written a HSC exam. I've looked at a lot of HSC exams, so that I have a pretty good idea of what is, or even, so it's entirely possible. I mean, I ate a hat once because I said there weren't any questions on back EMF, right? And the thing is, even though I ate that hat, I still stand by the fact that there was one question about back EMF 10 years ago or 11 years ago, something like that, which was in the old HSC before the syllabus update. And when there's 1 mark on something 10 years ago, you got to think, well, there are some kids who don't know how to do trusses. Now, that's a bit of a tough thing for me to say to you because you guys haven't done trusses yet. So I keep talking about trusses like they're a boogeyman. But the fact is that learn the easy stuff before you learn the hard stuff. Like, worry about learning the stuff that is guaranteed to be in the exam. If you are still uncomfortable with drawings, you probably don't need to worry about compacted graphite cast iron, because we should worry about the things that are likely to occur, not the things that. I'll give you and the thing they say in medicine is that when you see a patient with with a set of symptoms, you should think of horses, not zebras, right? Sorry, I left out a key detail. When you hear hoof prints like clop 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 clop, that's a terrible sound of hoof prints. I don't know if that was probably even worse. Anyway, the point is you should think horses, not zebras. You should think of the thing that is likely to happen, not the thing that's unlikely to happen. In this case, what I'm kind of saying is you should worry about the questions that are frequent and not the questions that are infrequent. And so that's why, I mean, I'm not telling you to not do those questions, but I'm just saying that where you should focus your attention in your study on should be the things that are likely to come up. Probably the best one, the question I think is maybe the most interesting out of this is the stopping distance question. So much so that I made a GIF. I've only made 1 or 2 GIFs in my time as a teacher, and that stopping distance thing, I think, when I figured that out, I'm like, that's not bad. That's a pretty good question. So, by all means, work on whatever you think is relevant. If you think that, hey, I think that Punsett's wrong, and I've actually seen lots of other questions that are on cast iron, first of all, let me know. I'm not perfect, and I've been doing this for a while, but there's definitely areas for improvement, and there are people who have been doing a lot longer than I have. Let me know. But then after that, by all means, you can study whatever you think is relevant. Okay, with that, I think that's an hour's of recording. The next lesson I think will probably be I'll probably do a half an hour Zoom with each of the 2 classes, just so that I can get some feedback from people and have people talking about things. I was still really planning, even on this lesson, to do the AutoCAD, but I am currently on this page of AutoCAD. And I'm just thinking, like, I wonder, because I used to be able to use the school one, right? So at home, I haven't downloaded AutoCAD. I didn't have any need, and I'm like, oh, I wonder what I'm going to do to prove that I really am a teacher while I'm at home. So because I can't take a photo of a badge or anything because I'm not at school, but that's for me to worry about. That will be what I'll do next. But I think next time what I'll do is I'll do half an hour of Zoom with each class, and it will be more just a catch up. I'll be interested to hear what TV shows people are watching, what everyone thought of the Loki finale, for example, and I'll set what homework we're going to be doing, because at this point we know that lockdown is going to go at least till the end of. Thanks. I haven't watched it yet, so I'll it's good to hear that it's a strong finale. I'm probably going to watch it today. Not a fan. Yeah, no spoilers. So, okay, different things. That's my plan. So I'll be working on AutoCAD sometime soon. I might even, if I'm feeling, because my days really have no meaning anymore, I might even do some. I'm probably more likely to do bonus year 12 on the weekend, but. It's possible that I might find that I'll take a crack at some drawing on AutoCAD on the weekend. But what we should probably plan on at this point will be the next lesson will be Zoom, and I'm going to set that up as a scheduled meeting when I close up here. Okay, well, I really appreciate the comments, guys. Just it does make me feel like I'm not talking into the ether, and. Yeah, have a great weekend, whatever that means to you. I've got my second. I'll leave that there. Okay, have a great day, guys. Enjoy your weekend.